Okay, hello ladies and gentlemen. We're going to talk a little bit about AC and how it's used in household electricity. But also this is industrial. Well, it's close to industrial, not quite. This is normally how household electricity works. This is 120 volts at 60 hertz, and that's in the USA. And they're 180 degrees out of phase. This is negative, this is positive, neutral, white wire, black wire, or red. Depending on how you wire things up, your hot wire can be black or red. These are hot wires. They're both hot. And the color code is so we don't kill ourselves, frankly. So ordinary light bulbs and the like will be connected right here, across 120 volts. And there's two phases that come into a house. They both are in different circuits. Now for your washer, dryer, air conditioner, ovens, things like that, this is 240. There's a potential difference of 240 volts between these two lines. And this is what you have your AC on. Dryer, a heater, oven, and so forth. And this is typically at 15 amps. Your 120 volt circuit is at 15, but the circuit's capable of delivering more. These circuits can be 30 or 40 amps, 30, 40, or even 50 amps. And it depends on the circuit breaker box, you know, what it's wired for. So, okay, let's keep going with it. So this is how it's modeled. Impedance on the two phases of the incoming line. And you'll notice the way it works, the positive current goes through here, the positive current goes this direction, so we have one current going one way and another going another way. If the drain on both halves is equal, then the neutral current is 0. A more complete model of what's going on. So we'd solve this by superposition. The technique of superposition. So this problem in general has to be solved by superposition, and that's where you, oh come on, why isn't my slide working? There we go. So you turn one source off and find the solution. Then you turn the other source off and find the solution, and then you add the two solutions together. So this acts like two sources. And that's why we fool around with two sources, by the way. It's very common. 3-phase is common in industry. 2-phase is very common in residential. And there are 2-phase motors out there. There's 3-phase motors and devices. There's single-phase motors and devices and the like. That we need to know how to do this stuff, even as mechanical engineers, where these things run motors. Okay, let's move on. And that neutral current is 0 if it's truly balanced. If these are equal, if these loads are equal and these loads are equal, you've got a symmetric situation. Most of the time you don't. If you're running an industrial machine, you probably do, because it's going to come straight from the circuit box right to your machine. Okay, here's the situation. What's the energy use at the rate? And this should be pretty easy. So you're just adding up wattage. This is not an issue. How many amperes total are being drawn, and here's the graph of when everything's on. Okay. Let's see. So lights, 1 amp, that's 0.12 kilowatts. So how much wattage it drains over 8 hours. And let's see, lights on from 6 a.m. to 2 p.m., which would be 8 hours there, plus another 3 p.m. until midnight. That's a 9 hours. Is that? Let's see. Oh, 5 p.m. Excuse me. 5 is here to midnight. 7. So there's how many kilowatt hours the lights take. This is pretty easy stuff. Let's see, the range, 2 hours plus another couple hours. This is the easy part. Stereo, just read off the graph how long it's on. 6 to 11, 5 hours here. 9 to midnight, another 3. Okay. Add everything up, and that's how much it's gonna cost. How much, and then you can figure out the amperage also. So what they're gonna do here, you've got all the amperes and your 120 volt sources. So we're asking how much do these two sources supply? That's the idea here, to verify. And it's just an outline to verify. So how much you're supplying should equal how much you're consuming. And it's a verification step. It's just a second way to check if everything makes sense in this problem. Okay, safety. With devices, so this is the white wire, the neutral circuit breaker, this is the red or black wire, the hot wire, the neutral wire. Now it says the ground conductor is connected to neutral, which is not actually true. The neutral is a return current wire. There is actually an earth ground here. And there might be some resistance between here and here. That's where you can get shocked. So if you grab your hand on the hot wire and to the neutral, it's very dangerous for you. Hand here to ground is also very dangerous. But the neutral all by itself is also kind of dangerous, because it can have a potential that is not near your earth ground. And of course, you're standing here. You're standing on your earth ground. And this is literally a chunk of metal driven into the ground just outside your house. That is truly an earth ground. And you're at the same potential as that, where you are. This tells us what happens when various things, you get amperage through your stuff. Remember, the outlet is 15 amps. You'd get burned. I like to make a hot dog maker by getting a couple nails and connecting it to the hot wire and the neutral wire of a electrical outlet, and sticking a hot dog in it. And you see the hot dog sizzle, and you know, and you can cook hot dogs this way and go eat the hot dogs. It's a hot dog cooker, but just remember, hot dogs are made out of the same stuff that you are. So just imagine what would happen if you stuck that through you. You would cook like that hot dog. Even at a lower amperage, you can have heart stopped, fibrillation, and it could be fatal, breathing stops, muscle paralysis, and so forth. Down here it's painful. This is where you get your electrical, your zap, things like that. That's why they say when you're in a fire, close your fists, because if you run into an electrical wire, your muscle will jerk back. But if you're open palmed and you grab an electrical wire, your fist will close around it and it'll make it worse. Get back. Okay, I'm gonna stop here, pick up next video after that.